All right. Newton's third law. Every action has an equal and opposite reaction. Okay? This is the most often misquoted and misapplied physical law there is. Because for some reason people think it applies to sociological situations. Okay? Like interpersonal interactions and things like that. And it has no place in there. Right? People like, you say something really mean and you get slapped in the face. No, every action has an equal and opposite reaction. No, he got slapped in the face because you were a jerk. Okay? I'm not saying that's appropriate, but it also wasn't opposite. Okay? So yeah, don't try and apply it to those kinds of situations. It really doesn't fit or apply to those situations. Okay? It does, however, apply to the face slapping part. Okay? So, if you're like Will Smith, too soon for that? If you were to smoke somebody, okay, slap them, punch them, kick them, whatever, okay, when you exert that force on them, is there a possibility you injure yourself?
Yes.
Yes. Okay. One of the most common injuries to martial artists and anyone that does combatives, okay, is that they can injure or break the bones in their hands or feet. Okay. It's actually why a lot of martial arts focus on striking with parts of the body that are heavier. Okay, I mean that also can do more damage, okay, to the person you're striking, but it also results in less likelihood of you hurting yourself. Okay, if you punch someone with your closed fist, you're very likely to break fingers or your hand. Okay, because the bones in your hand itself is a small mass, but you're hitting something that's more massive. Okay, like if you get angry and hit the wall, which by the way is really stupid. Okay, but people do it for some reason. Okay, you're going to break your hand. The wall is way more massive than your hand is. Okay, and the force that your hand exerts on the wall is equal to the force the wall exerts back on your hand. That's Newton's third law. What's different is the acceleration the wall experiences versus the acceleration your tiny hand will experience. Okay? It's much greater because the mass of your hand is much smaller, and that means you're more likely to break bones. Okay, so as I was saying, a lot of martial arts focus on using things like the forearm, the elbow, the knee, okay, the shin, as opposed to the foot or the fist, because those things are likely to be injured when striking. Okay, so it's something we look at. Also, if you're in any kind of contact sport, okay, you want to, if it's a contact sport where you're actively hitting someone like football or hockey, okay, you don't hit them with an extremity. Okay, like if someone's running by you and you want to tackle them, you don't reach out and grab them with your hand. That part of you isn't very massive. You get in front of them and you put most of your mass in front of them, okay, because that way you can experience less acceleration. Okay? If somebody's running at a full tilt and you just stick out your arm, okay, unless you're really strong and braced really well and you can clothesline them, okay, they're probably just going to they're just going to go right through that. But if you're standing in front of them and you reach out and hit them, okay, and you get them with your shoulder like you're supposed to, okay, in any type of hit, you're going to be more effective there because more of your mass is being used and you experience less acceleration, they experience more acceleration, okay, because you're exerting that force. Does that sort of make sense? Okay.
Does that have any relation to like static friction and kinetic friction? Like, when you say like force, acceleration, like they would have more acceleration than you would. Is it because you're like static, like you're standing still? Like, does that contribute to it?
Well, it certainly, they would still feel that. Like even if I was in space and I was weightless,
yeah,
this would still apply.
Okay.
When you have friction, you are better able to brace yourself.
Okay.
So if I'm braced properly and I hit someone, it's not just my mass, it's the mass of everything I'm braced against as well, right? So if I'm against a wall and somebody hits me, it's me and the wall, right? That's way more mass. Yeah. Okay. All right, so we have to understand that according to Newton's third law, all forces act in pairs. There's never a case where one force acts and it's all alone. Okay? If something pushes on something else, that something else pushes back on something. Okay? That's what always happens. Right? Right now, as I'm walking, okay, I push on the floor, okay, and I push the floor backwards, and the floor pushes me forwards. Okay, now the floor is attached to the earth. So I accelerate this way. What happens to the earth?
Accelerates the opposite direction.
It does. Does it matter? I don't exert very much force. Okay, the earth is incredibly massive. Okay, 5.2. The 5.2 something times 10 to the 24 kilograms, 5.28 or 5.29 I think it is, times 10 to the 24 kilograms. It's big. Now, this whole idea that the earth accelerates when I push on it was misapplied horribly by Nike. Is that what you were gonna
No, I was just gonna say, like, everyone has the theory that if everyone jumps at the same time, like, the earth would move. I was like, would that actually happen?
No.
We don't have to be stupid.
And we're going to do an activity on that later, not today, but later.
Like hypothetically, if everybody in the world were to accelerate one direction, would the Earth like technically like move, like accelerate the opposite direction? But I guess if it's round.
You mean,
Like if
so no, you could not make the earth accelerate its turning by getting everyone to run in the same direction. No, you couldn't get everybody to jump in the same place at the same time and knock Earth out of its orbit. Okay? And the reason being is not that there wouldn't be an acceleration produced or that a force wouldn't be exerted on the Earth. The Earth is just huge. And it just wouldn't experience anything that would matter. Okay? The mass of the entire population of the Earth is a fraction, a very tiny fraction of 1% of the Earth's total mass. Okay? And so it just doesn't have any effect. Plus, that also assumes the Earth is perfectly rigid. Is the Earth perfectly rigid? In fact, the crust, which is what you'd be exerting the force on, floats on the mantle, which is magma, which would also then, sort of partially nullify the effects of any force that you put on. Okay? And so, yeah, it just doesn't work. Theoretically, yes, something happens, but practically speaking, not enough to do anything. Okay, would be the answer there. All right. So, with Newton's third law, okay, every action has an equal and opposite reaction. When you blow up a balloon and let it go, that's Newton's third law, okay? The thing that makes it go around the room, okay? When you blow into it, the air inside pushes on the inside of the balloon, and the balloon pushes back. So when you let it go, okay, they exert a force on each other, okay? And that actually propels the balloon in the random pattern and whatever it goes in, okay? Rockets, same thing, okay? The force of the engines pushes on the rocket, but the rocket pushes on the fuel, okay? And that is what makes it go in opposite directions. Okay. All right. Everybody okay with that? So when you push on something, you feel a force. So if I stand here and I push on the wall, what will happen to me? I'll come backwards. Okay? Did the wall move? It did. Didn't you hear it? The board cracked. Okay? So when I push on the board, okay, I get a little flex. The board flexes a little bit. Okay? I move backwards. Okay? This wall is pretty solid though, right? It's connected to the floor, which is connected to the earth, which means basically nothing else is going to happen. Okay? Doesn't mean there wasn't an equal and opposite force there. Okay? It was still there. All right. Could you do this? If you're stuck in that boat for whatever reason, you didn't bring paddles, okay? And you're in that boat and it's not near the dock, could you run along the boat and jump off and land on the dock? Why not? Okay, the boat's going to move backwards. Absolutely, the boat's going to move backwards. The boat moves backwards because you push backwards on the boat. What's the boat do? Pushes on you. You should be able to do this. Okay? Now, if you're really far away from the dock, all you're going to get is your teeth embedded in the dock. But okay, if you do it right, you should be able to jump from the boat to the dock. The boat will move away from the dock while you're pushing on it. Okay? So if I want to maximize my ability to jump, which way do I push? Right, I want to push backwards and down. If I just push down, I just jump straight up. That's not going to help me, okay? But if I want to maximize this force, I want to push not only backwards, but a little bit downwards as well, because when I push a little bit downwards, now it's not just the mass of the boat, it's the mass of the water under it, okay? So it will move less, right? The boat will go down into the water a little bit, but it won't go backwards quite as much, right? Even if I didn't do that and I just ran backwards or ran forwards while the boat moved backwards, I should still be able to do this because the boat is still going to push me forwards. Okay? And it's likely, okay, that my mass is probably greater than the boat. So my acceleration will be smaller than the acceleration of the boat. It still doesn't mean the boat doesn't push on me. The boat totally pushes on me. Okay? And I get an acceleration in the opposite direction. Okay? It seems like, no, this wouldn't work, and probably you'd have to be pretty coordinated, because if you've ever like stood up in a boat, okay, especially a small boat, that's not the easiest thing to do, so certainly running down the length of a canoe, especially with the seats in place, is, going to be a test of your, kinesthetic abilities, but it is possible. It's certainly possible. Okay, so that's the action-reaction law. Okay, every action has an equal and opposite reaction. Right? That reaction, though, is based a bit on mass. Okay? One object, unless those objects are of equal mass, one object is going to experience a greater acceleration than the other. Okay? So when we were talking about like collisions back at the beginning of the unit, right? Smart car and a semi-truck, head-on collision. Forces are equal. Yeah. The amount of force exerted on the smart car and the amount of force exerted on the truck are equal, but opposite. Okay? But what's different is the smart car has a much smaller mass than the truck, so its acceleration is much greater than the truck, which is why it sustains more damage. It's not about the force, it's about the acceleration that that force produces, and that is inversely proportional to your mass. Okay? So the smaller your mass, the larger your acceleration, and that's where the Newton's third law stuff really comes into play. Okay, has anyone ever used a firearm? Okay, what do you have to be mindful of when using a firearm besides don't point it at anyone?
The kickback.
Yeah, the recoil. Okay, we get this idea from movies that, anybody can, things like do this, right? People get this, like, no. I mean, you might be able to do that, but your accuracy would be pretty lame, okay? If you're using a weapon and you're trying to actually hit a target accurately, you need to brace for the kick, or for that recoil. Where does that recoil come from?
The opposite force of the bullet.
Yeah. When the hammer strikes the round and detonates the gunpowder, the expanding gases push forward on the bullet, which has an incredibly small mass, okay? And the bullet pushes back on the gun, okay? Which has a much larger mass. And if you have the gun braced, so if it's a rifle and you have the butt against your shoulder, not this far from your shoulder, okay, but right against your shoulder, now it's kicking all of that mass, and so you can absorb that and you don't get the gun doing, well, dangerous things, okay, like moving in a wild direction, right? But that's where the recoil comes from. It's a Newton's third law situation. All right, so here's a very simple kind of Newton's third law type of situation. So if you're in space and you're, moving along your spacecraft, if you push on the spacecraft, what happens? And the spacecraft goes the other way. Okay? Both of those things happen, but we always look at it like, well, yeah, I would fly backwards. Yes, you would. And the spacecraft would go the other way. As much?
No.
No, because it's way more massive. Okay? Its acceleration will be a great deal less. How long does that acceleration last? While the force is being applied. So if I'm right up against the ship, as long as I'm pushing, the acceleration happens. As soon as I lose contact with the ship, now we both move at constant velocity. Whatever the final velocity of that acceleration was, that's now the velocity that we have. Okay? For the spacecraft, it's not very much. Okay? And whenever we send a spacecraft somewhere, we don't need a lot of force. okay? All the spacecraft we've ever sent had actually fairly small engines, right? All they did was just make corrections well ahead of time, okay? Because they can only produce very small accelerations, but if you do it well ahead of time, it's enough. It can make a huge difference by the time you reach your destination. All right, so looking at this one here, we've got the astronaut who has a mass of 92 kilograms, the spacecraft, which is 11,000 kilograms, and the astronaut exerts a force of positive 36 newtons on the spacecraft. Okay, so find the acceleration of the spacecraft and the astronaut. So here's what we have to know about this situation. The force on the astronaut is negative the force on the spacecraft. That's what Newton's third law looks like when you write it out mathematically. Every action has an equal but opposite reaction. So the forces are equal, but one of them is negative. Okay? All right, so what that means then is that I can calculate the acceleration of the astronaut, because I know the force being exerted on the astronaut is negative 36 newtons. Right? So all I have to do then is a very simple Newton's second law calculation now. Okay? And that is that the force exerted on the astronaut divided by the mass of the astronaut equals the acceleration of the astronaut. So negative 36 divided by 92, right, gives us a pretty small acceleration, like 0.3? Okay, so 36 divided by 92. All right, 0.39. Negative 0.39 meters per second squared, or 0.39 meters per second squared backwards. Right? But when I do that same calculation from the spacecraft's point of view, okay, so the acceleration of the spacecraft, okay, force on the spacecraft divided by the mass of the spacecraft, it's positive 36 newtons now, but it's divided by 11,000 kilograms, okay, which is obviously much, much bigger. Is that pretty small?
Yeah.
Like really small. That's 3.3 millimeters per second squared. Okay, that's negligible, really, unless that spacecraft is on a predetermined course. Then that tiny little acceleration, for as long as it lasted, could have made a fraction of a degree difference in its course, which means if it's traveling a really, really long way, by the time it gets there, it could be way off course. Okay? I mean, if it's only got to travel, let's say, so this is its original course. Okay? And if I just give it a slight nudge by pushing off of it, okay, and that's not very far, well, it doesn't make a huge difference. But if it's going a really, really long way, by the time it gets there, the difference is getting bigger and bigger and bigger. And these are the kinds of things that the people at NASA who do all the course stuff, okay, have to take into account. So like, what's his name, Glover, he played the astrometrics guy in The Martian, okay, who figured out that the Hermes could do the gravity assist slingshot and get back, okay? Those people, that's what they deal with. They deal with those fractions of a degree that everything could make, okay? They have to analyze those courses, and they have to say, we're gonna fire the engine, we're gonna turn the spacecraft this much, we're gonna fire the engine for this many seconds, and it's gonna make this tiny little difference in our course, okay? And if we're off by even the slightest amount, we maybe don't make orbit, okay? Or something like that, or we crash into something that we weren't supposed to.
If you're inside the spacecraft and you push on a wall, you wouldn't go off course, right? Or if you moved any force inside the spacecraft?
If I'm inside the spacecraft, so inside the International Space Station, let's say, and I push on the wall, I come off the wall.
I mean, if you like.
No, if you're in
were-
space and in a rocket, like,
Like, can you build up enough momentum, like running to the side, if I ran from one side and then hit the wall?
Okay, running would be different.
Okay, well, like.
Because if I'm running, then I've got artificial gravity,
Yeah.
And as I'm running, I'm already pushing on the spacecraft,
Yeah.
right? But I would say that would be negligible in the long run, mostly because you're actually the same mass. So that action-reaction pair is gonna make a bunch of difference,
That
right?
makes sense.
Yeah, but if I'm like outside the spacecraft, that push can make a difference. I'm no longer connected to that. If I'm inside the spacecraft, I'm still connected to it. So it kind of works like this. I always tell people that if you become an astronaut, remember what I teach you today. If you become separated from the spacecraft, always make sure that you've taken something heavy with you, a big heavy tool, a wrench, something. So that if you're separated from the spacecraft, all you have to do is take that wrench and push it. Because when you exert the force on the wrench exerts the force back on you, right? And you'll go the opposite way. At which point, I often have people tell me, well, then I wouldn't let go of the wrench. And then I point out to them, well, you have to. Because if you don't, you exert a force to get it moving, and then you exert a force to stop it. And all you're doing is sitting out in space going like this and accomplishing nothing, because the force you exert to move the wrench and then the force you exert to stop the wrench cancel each other out, and you just look silly out in space. Okay? If you want to get that acceleration, you've got to throw the wrench and then go back. So if you stay in the spacecraft, you have to stop by hitting the other wall. Well, that's going to cancel what you did in the first place, right? So you have to become separate in order for the effect to be there. That's why shooting the engines or firing the engines has that effect. It's getting rid of that massive propellant. That massive propellant is now gone, and so that action-reaction happens. Versus if they keep the propellant inside, it just bounces around inside and does nothing.
Yeah.
Yeah. Okay. Everybody all right with that? Kind of how that works? Yeah. All right, so that was what we just did. That was our reasoning, and that was our math. Okay, so we've already done that. Now, this is what we just talked about. If we're walking, okay, we exert a force on the Earth. Earth exerts a force back. We propel forward because our mass is so much smaller than the Earth's.
Can I go to the washroom?
Okay, but the amount the Earth accelerates is negligible just because of the Earth's mass, and the Earth isn't perfectly rigid. You've got the mantle, all of that kind of stuff. So in the end, it's not something we have to worry about. Okay, now, can the force of the moon move the Earth?
Yes.
Yeah, it does all the time. Okay, it causes the tide, pulls the ocean. Okay, but it also makes the Earth wobble back and forth in its orbit. Okay, the Earth pulls on the moon pulls on the Earth. Okay, and as the moon moves around, it actually pulls the Earth with it a little bit. Okay, it's actually how we discover other planets. Okay, like exoplanets that are around other stars. We look for the wobble in the star. We can't see the planets; they're too small. Well, actually, now we can. With James Webb Telescope, we can. But okay, before all we did was watch stars to see if their light changed. Okay, if their light changed, it was either because they got dimmer because a planet moved in front of them, between us and them, or because the planet pulled them one way or the other and caused a shift in their light, a Doppler shift in their light, moving towards or away. And we have sensitive enough X-ray telescopes that we can detect that. If a star wobbles a lot, we can figure out how much is around it.
So how come it pulls? Like how come the moon and the Earth pull? Like it's like
They both have mass, and as a result, they both have gravity. So you can exert gravitational pull because you have mass. So anything that has mass has a gravitational field, no matter how small.
okay.
Now, my gravitational field is so incredibly small that I don't ever see anything like come to me because of that, right? Theoretically, if I kept eating and got bigger and bigger and bigger, eventually food might come to me on its own. But probably not, because the Earth is just so much more massive,
Okay.
right?
And then, but there's different. So the different gravitational pulls of different planets depend on the mass of the planet.
It depends on mass and it depends on distance. So the
Distance
closer
on
I
the
am to Earth, the more attracted to it I am gravitationally. So if I go further away, I'm actually less attracted gravitationally to it. And you can actually detect that at various places on Earth. So if you're at the equator, you actually weigh less because you're less gravitationally attracted to the Earth than if you're standing at the North Pole. Because the Earth's not perfectly round. It's also not flat, because that's crazy. Just in in case there's any flat earthers. If you're a flat earther, you should probably drop my class. Yeah, that's crazy dumb. Okay. All right. Here's an application that we use for Newton's third law. Okay, you've probably all seen this at some point. The person who's got the U-Haul trailer, like attached to their Honda Civic, and they're cruising down the Deerfoot at 120, even though there's stickers all over the trailer that say maximum 80. Okay, but they do it anyway. Now, U-Haul recognizes that most cars do not have a brake hookup. Okay, if you have a pickup truck, they usually come with an electronic brake controller and a brake hookup, so you can just plug it in and electronically apply the brakes on the trailer. Okay, but a small car like a Honda Civic doesn't have that. Right? If it has a trailer hitch at all, it certainly doesn't have an electronic brake hookup. So it uses Newton's third law to apply the brakes. Inside the hitch, okay, or on the hitch area, is this actuator. And what it does is it uses a bit of Newton's first law and a bit of Newton's third law to apply the brakes. If I don't have anything, if I just have a trailer with no way to apply the brakes, when the front car stops, what does the trailer do? Right, it pushes on it, okay? Because this is a pivot point, if that is abrupt, the trailer can jackknife. That's Newton's first law, right? It'll just come right back around and swing right around and hit the tow vehicle. Okay, so if we have a brake actuator, when the trailer starts to move forward and push on the car pushes back, which applies the brake. So it's a spring-loaded mechanism that relies on Newton's first law to initiate Newton's third law. Okay, the trailer keeps moving forwards and pushes on the tow vehicle, and the tow vehicle pushes back, which applies the brakes. It's not great. It's not going to stop a jackknife. If you just had to pile on the binders, that's not going to do it. Okay? But if you're driving in a reasonable fashion and being careful, this works really well. Okay? Especially for a vehicle that would not have any other way to apply the brakes on a tow trailer. Okay? That sort of makes sense? So it's a good thing to have when there's no hydraulic or electronic way to actuate the brakes on the trailer. Okay. All right. All right, so we're going to look at a couple of Newton's third law examples, and they involve boxes pushing on boxes. Pushing on boxes sometimes. Sometimes it's 2 boxes, sometimes it's 3 boxes. Okay. All right, I want you guys to write this one down. So we got 3 boxes. Okay, they all have different masses, but they're all in contact with each other as shown in the diagram. Okay, so here's the good news about Newton's third law. There's no formula for Newton's third law. Okay? There's no new mathematical operation we have to learn to solve the Newton's third law problem. Newton's third law defaults to Newton's second law. Okay? All we have to remember is that this force is going to have an oppositely directed force, and then we just do sum of all forces and m times a. Okay? These all break down into Newton's second law problems, which is why we don't spend a lot of time on Newton's third law. They're really just system questions. So I've got these 3 boxes, A, B, and C. I know the masses of them. Okay? And someone pushes on box A. Do all 3 boxes move? Yes. Okay? Especially since they're on a frictionless surface. Okay? So all the boxes accelerate at 1.5 meters per second squared to the right. Calculate the force that exerted by box C on box B. Now, when people first read this, they're like, what do I do here? Like, I have no idea what to do here. Okay? Well, what we do is we look at each box. Okay? I mean, we know that as a system, they have this acceleration, which means I can calculate the net force on the system and the net force acting on each individual box. Agreed?
Yes.
Which box has the least number of forces acting on it?
C.
C. Because C doesn't have anything in front of it. Okay? Box A has the force applied from the hand and the force of B pushing back. Box B has the force from A acting forwards and the force from C acting backwards. But box C only has the force from box B. Now, you're probably going, so how does that help me? They want the force that C exerts on B. I think the light went on.
It's the same.
It's the same. Okay, box B pushes on box C, but I don't know the force A exerts on B, so I can't use B to calculate that force. But C only has one force acting on it, and it's the force that B exerts on it. So the force that C exerts back on B is equal to that force. So, here's what I'm going to do. I'm going to look at box C, which is 5 kilograms. The only force acting on box C is box B. That force is equal, but opposite to the force they want me to find, which is the force that C exerts back on B. Okay? If I'm looking at box B, okay, those are the three boxes. If I'm drawing free body diagrams of the three boxes, it's frictionless, so I don't have any friction. Okay? Box A has the applied force from the hand and the force of B acting back on it. Do I know either one of those forces? I don't know either of those forces. I have no way to calculate either of those forces. All the question told me was the acceleration. So while I could find the net force acting on box A, it won't do me any good because I don't know either of the two forces that add up to it. So this, box A, useless for this question. In addition to the fact that this is the force they want me to find, and that's not even acting on box A at all. Okay? So box A, completely useless to me. Okay? Box B, while having the force the question wants me to calculate, is also useless because I don't know the force A exerted on it. All I can calculate about this box is its net force, mass times acceleration. Since I know neither of the two forces that add up to that, I can't use that box either. Box C has only one force acting on it, which makes that force the net force. Can I calculate the net force?
Yes.
Yes, because I know the mass and the acceleration of box C. Okay, so that's going to be 5 times 1.5, and that's going to be 7.5 newtons. Okay, and that's going to be forward. Okay, the only reason that that force is there is because B exerted it on C. So what did C do when B pushed it? Pushed back.
Wouldn't it be backwards then?
But yeah, that's the force, that's the net force on C. It is forward. The force they want me to calculate is opposite.
Okay, so
That
then your
force.
answer would be 7.5 newtons back.
Exactly.
Okay.
Okay? So all I have to recognize is that because B caused this force, the force that C exerted back on B, this force right here, is equal but opposite to that 7.5 newtons forward. How intuitively complex is that question? Like, we did one mathematical operation, and that question took us nearly 10 minutes. Because there was a lot to think about in that question. That's what makes a Newton's third law question hard. Okay? The math, I multiplied two numbers together. That was it. That was all I had to do. Okay? But I had to figure out what two numbers do I add together. How do I get the force I'm looking for? By finding another force. Like I swallowed the spider to catch the fly. Okay? Like that's what this comes down to. You're always doing something to get something else. Okay? That's how Newton's third law problems work. Okay? Mathematically, pretty simple. Okay? But figuring out what math to do is challenging. All right, so situation from the previous example. All right, so all the stuff we just did. Now we want to figure out the force that box B exerts on box A. But we can use the force we calculated in the last question. Right? So we know these other forces now. We know the force that B exerts on C okay? That's what we figured out. Okay? We also still know that the acceleration of this system is 1.5 meters per second. Okay? So we're trying to find the force that B exerts on A. So do you need to break this down into individual boxes again? Yes, you do. Because this is a force acting on a single box. Okay? It's not asking about the system. Okay? I have to break this thing down and isolate a particular box. Your first challenge is to figure out which box you need to isolate so that you can find that force. You may not actually be finding that force, spoiler alert, you may be finding a force that is equal but opposite to it. Give you a few minutes. Which box should I use? Can't use A. Don't know
Oh,
enough
no,
about
yeah,
A.
sorry.
B. I have to use box B. Okay? And the reason I have to use box B is because I was actually given one of the two forces that's acting on it. Because I calculated it in the last question. Okay? There's this force. This is the force that A exerts on B. Okay? And this is 10 kilograms. And then there's this force. This is the force that C exerts on B. And it's 7.5 newtons. Because I calculated that before. I don't want this. Okay. So I've got those, I've got that force. What else can I calculate about box B? The net force, yeah. I know the acceleration is 1.5 meters per second, and I know the mass. Okay, so the net force on B is going to be 15 newtons, 1.5 times 10. And it's positive. Okay, so now I know the net force, and I know one of the two forces that contributes to it. Can I find the one I don't know?
Yes.
How does that help me? That's the force that A exerts on B, and the question wants the force B exerts on A. It's the opposite. Okay, that's an action-reaction pair. The force A exerts on B is equal but opposite to the force B exerts on A. As long as I can recognize those action-reaction pairs, I can go, well, I can't get the force they want, but I can get the one it's equal to, and then I solve for that one instead. Okay, so for this one here then, I'm going to say that the F net on B is going to be 7.5, which is negative, right, plus the force of A on B. Okay, and since I know the net force on B, I just take that 15 newtons and I subtract negative 7.5, and that will leave me with the force of A on B, which will be 22.5 newtons in a forward direction, which means the force that B exerts on A is backward, 22.5 newtons. Okay. So Newton's third law questions are usually systems, okay? And as long as we can recognize that every action has an equal and opposite reaction, we can usually figure out what force we have to find. Okay? But it's very, very convoluted. Okay, questions on what we did there? Okay. All right, so this one's only 2 boxes, okay? They're different masses, 6.5 and 8.5 kilograms. They're placed next to each other, so they're in contact with each other on a rough surface, so there is friction. An applied force acting on box A causes both boxes to accelerate at 2.6 meters per second squared to the right, which I'm going to make positive. The magnitude of the force of friction on box B is 28.3 newtons. Calculate the force exerted by B on A. All right, I'm going to give you a little bit of time on that one. Okay? Which box should you use? B. Yeah, you have to use B here in order to solve this one, right? Because you don't know how much force is being exerted on A by the hand. Okay? Without that piece of information, you can't use A. All right, so definitely use box B. Okay? And you also know the force of friction that is acting on box B, so that's also helpful. So as we just said, if we're going to solve this, we have to use box B. We don't know what the force of friction is on A. We don't know the force the hand exerts on A. We have no information on A except its mass and its acceleration, which isn't enough. Okay? So we're going to use box B because we know more about it. Right? We know its mass is 8.5 kilograms. We know it's being pushed by box A. Okay? So this is the force of A on B, which is equal to, but opposite, the force that B exerts on A, which is what the question wants us to calculate. Okay? So if I can solve for this, then I'll know the force that the question wants me to solve for. The other piece of information I have is that this force here is 28.3 newtons and represents the force of friction. Okay? I can calculate the net force that is acting on box B right now because I know both its acceleration and its mass. So we'll have 2.6 times 8.5. It's like 22.1 or something. Okay, so 22.1 newtons, and that's positive or to the right is actually what they give us in the question. All right, so I know the net force, and I also know that the net force is the vector sum of all the forces acting on box B. Is this just like every Newton's second law problem we've ever done? Oh, I did m times a, now I'm doing vector sum of all forces. It's always the same. Okay? Newton's third law is really just Newton's second law. Okay? Just at the end I have to remember, oh right, it's opposite. Whatever I calculated is the opposite of that. Okay? So I've got F net, and I'm looking for the force of A on B, so I'm going to subtract that force of friction. So I'll have F net minus the force of friction equals the force of A on B. So that'll be positive 22.1 minus negative 28.3, which gives me 50.4, right? Positive 50.4 newtons. So the force that A exerts on B is 50.4 newtons to the right. The force that B exerts on A is 50.4 newtons left. Right? And that's our final answer, 50.4 newtons left. That's the force that B exerts on A. All right? In terms of how difficult mathematically that was, there wasn't much to it. Certainly nothing that we haven't done 150,000 times, well, probably not that many, but a bunch of times already using Newton's second law. Right? We just have to be able to apply it to a new situation. Okay, I think rather than, I think we'll look at this one probably on Friday because we're doing our friction lab tomorrow. Okay, so friction lab tomorrow. We won't need the SparkU app for this one, but you will need the clinometer on your phone. Okay, because we're going to be measuring angles this time. We're still going to be using the ramps, but we're going to be using these masses in wooden sleds. And we're just going to lift the ramp up, and we're going to do a friction lab with that. All right, so that's what we'll be doing tomorrow. trying to decide whether I should do your quiz tomorrow or not.
Nah.
It's only 5%.
You know what, I'm gonna hold off on the quiz for tomorrow.
Thank you.
Just because we've just talked about Newton's third law, and I really don't need to assess Newton's second law for like a fifth time, so. No quiz tomorrow, we'll get the whole class to the lab tomorrow. Just be ready to do it so that you can get as much of it done in class as possible.